All right, so if you happen to be at home and you're reading some of this, and even if you're sitting here and reading this, it's going to sound like today you're working on reviewing Force and Motion. This is obviously something that I had to do when I was out of class last year, but the stuff inside of it is stuff that I would still want to do in the class, but I'm not going to go back and redo an entire Nearpod presentation and change a few words because I think that's just a waste of time. So we're still going to do some things. There's going to be some things that we skip. If you go back and watch this, or you happen to be one of the few people that are at home, it's going to be a very rough day on you because the majority of what we get is going to be conversations about the videos that are embedded in here. I can't play the videos on my website and then talk about them. It doesn't work that way because that's copyright laws, and I'm not going to lose my YouTube channel over something silly. We don't have time for that. So as we go through this today and we start to talk, it's going to be very tough for anybody that's at home watching this because they're going to miss the entire video. So they may have to watch part of my video and pause it and then go find the video that we're looking at online and then come back and then listen to what I'm talking about and look at the notes that we're taking. Otherwise, it's really not going to make a whole lot of sense. So we'll see how we can do. We'll try our best. So again, we're going to continue to look at forces in motion, and as we move to the next page, you all in here are going to have a chance to move through some things like in a VR nature in a skate park. And there's some people on bikes, there are some people on skateboards, and you can look all around, and you are going to quietly, hopefully you can get this because my last class sure didn't, quietly think to yourself, what different things from force and motion do I see inside of this picture? And I'm going to be honest with you, you can really find a lot of different things going on in that picture. And then we will come back together and chat with each other. What do you need, sir? And it better be related to force and motion. You to keep refreshing then. If you can't see it, then we'll figure it out. Everybody good? All right, so when you click the page to the next page, your page will look something like this. And you are able to use your mouse to click and drag and look in like 360 degrees. You can look up and down, but there's obviously not a lot going up there. Down here, just look around at that. And for the folks at home, I'm going to pause there. All right, so in the video, the young lady mentioned balanced and unbalanced forces. And when you talk about those, they are two of your vocabulary words this week. You'll notice that I added a small little tidbit to the end of the regular definition. That unbalanced forces are forces that do not cancel each other out when acting on an object. If you have unbalanced forces, you have movement. If you want to take this outside and put it in terms of the seesaw, which is what I think of when I start thinking about things being balanced, if someone puts more force on one side than the person on the other side, the seesaw is going to move. Would you agree with that? It's going to move down on one side and up on the other. And then if the person on the other side decides to then put more force than the other person, then the seesaw would move back again the other way. There are some pictures that I want to draw on here that are going to represent what we're looking at as well. Hopefully I can get in here and not mess anything up too bad. If I have a person pushing on this box with 50 newtons, that's what the N stands for, and I have a person on this side who is pushing in this direction with 20 newtons, obviously the person pushing towards the right is pushing with more force, correct? So the box would move in this direction. Newtons, you're going to see me write this 50 in. So when I write 50 in, this N stands for newtons. Newtons are a measurement of force. So when something pushes or pulls on something, it's pushing and pulling with a certain amount of newtons. It's pushing or pulling with a certain amount of newtons. And so when you have unbalanced forces, you have movement. So again, we just saw, we did this in class. We had somebody pushing on one side of a chair and me pushing on the other. They were pushing harder than I was. Therefore, the chair moved in the direction that they were pushing. She was using more newtons than I was, and there was movement. In the second example that we just did, when we were pushing, we were both pushing with the exact same amount of force. How do we all know that? We don't have anything to measure the newtons. 50 newtons, and she was pushing with 50 newtons. How do I know that? Because the chair that we were pushing on did not move. The chair did not move. There was no movement whatsoever. Now, Austin, one of the things that they love to put on the test and talk about a lot is typically not people pushing boxes. It's tug of war. Is one of their favorite things to use as examples of balanced and unbalanced forces. If two teams are outside and they are both pulling on the rope with the exact same amount of force on both sides, the little flag in the middle, if you happen to have one, is not going to move, is it? Neither team on either side is going to start getting, get drug across the grass like we do when we have field day, because the forces are balanced. They are equal. They are the same. However, what we see in almost every game of tug of war is this. One side pulls harder than the other. Therefore, they're exerting more pull than the other side, so the rope starts coming towards them, and eventually the flag that's in the middle crosses the certain point, and then the gym teacher declares that one side that pulled harder the winner, because there is movement. So balanced forces, no movement. Just think about going outside on a seesaw, right? If you're outside, it's going to be really hard to draw this on here, but if you're outside on a seesaw and it is like this, the seesaw is balanced. It's not moving. Why is it not moving? Because there's an equal force on each side. And we can just call that 5 newtons, and we'll call this one 5 newtons. And it's balanced. If you have unbalanced forces, and I don't have any more room to draw that because I wrote the definition of newtons in there, you are going to have movement. Does that make sense with balanced and unbalanced forces? All right, I'm going to pause. So as we were messing with our skateboarder on this page, we noticed when they were at the top of the board here, there was a whole lot of potential energy. As he would move, we noticed kinetic would go up. As he's sitting here on the ramp, more potential energy, right? Potential, I wonder if I can drop him in from here.
Yeah, you can. He goes flying off.
Oh, I have too much friction. No friction. Yeah. Dropping him from here.
He goes flying.
And he landed it. Little person do it? All right. All right. Little person, no friction, one time, drop them. And hey, Tony Hawk in the building. Anyway, back. Shh, back to this. Shh. There were 2 things that we saw on that page, and we spent a good deal of time in class talking about it. And right now you should be taking notes while I talk to my people that are not in here and they're at home. Kinetic energy. Anytime something is moving, like when you're in a roller coaster, it's a great drawing of a roller coaster, by the way. When you're in a roller coaster going down a hill, that is energy of movement. You are moving. That is kinetic energy. However, when you are at the top of the roller coaster hill, which we will take a look at in a video here in just a second, you have the potential for the roller coaster to start moving at a high rate of speed thanks to gravity, right? Potential energy is stored. Kinetic energy is the energy of motion.